Okay, welcome to note set number 11, where we're going to take this idea of Fourier series and make it even more powerful. So remember, Fourier series allows us to deal with periodic signals. Now we're going to be able to deal with non-periodic signals, but the basic idea remains the same. We're breaking a signal down into a superposition, a sum, of sinusoids, and the reason is that sinusoids go through a system in an extremely easy and understandable way. All we've got to do is figure out how the amplitude and phase changes, and we saw this idea of frequency response. That's what the system or the circuit does. It's a characterization of that, and we saw that in an example in the last set of notes. So let's get introduced to the Fourier transform here. So we're seeing here Fourier series for periodic signals, and we were dealing with complex sinusoids, and in particular, look at this, k omega 0. So as k goes through the integers, we end up with what are called harmonically related frequencies. Some fundamental frequency omega 0 and all the higher harmonics, 2 omega 0, 3 omega 0. So that phrase harmonics and harmonically related means start with a fundamental and you have integer multiples of that fundamental. But that can only give us periodic signals. What we need to do is be able to handle other things. So can we modify this to get non-periodic signals? And the answer is yes, obviously. We wouldn't be asking the question if not. So let's sneak up on this idea here and say, okay, so suppose we modify this instead of k times omega 0, we just add an arbitrary index, omega sub k, and now we have some infinite collection of discrete frequencies. They don't have to be related in any way, but there can only be discrete values. And the idea, or the thing that we see here is that although this will create some non-periodic signals, there are a lot of non-periodic signals that this just simply cannot create. And the reality is that we need a way to include all possible frequencies over a continuum. This idea just will not allow us to include all, because no matter how close we choose these frequencies, omega sub k, there's always going to be something in between those two. That's just a feature of the real numbers, and that's called on the continuum. So you pick two numbers on the real line, and you can always pick another one that's in between them. So we can't do it this way. We need some way to get all of those frequencies. So that brings us to an integral. So we had a sum before where we were summing. Jeez Louise. Try this. There we go. This is not working all that smoothly, but we were summing over frequencies. But if we integrate, so now we're letting our integral go from minus infinity to infinity, but we're going over omega, and so this thing, we hit all possible omega values, and when we look in here, we're now getting complex sinusoids. Omega is being swept through all possible frequencies as we do this integral. So we'll be comparing this to the Fourier series in just a little bit. And yes, this will work for, and I say any, and I say practical with some italics there. There are some signals for which this won't work, but the vast majority of signals we're interested in practice, at least in signal processing, communications, and things like that, this works really perfectly well for them. So this integral here is called the inverse Fourier transform. and we'll see in just a little bit where the non-inverse or just the regular Fourier transform comes in to play in this idea. So as I said, this integral replaces the sum that we had for the Fourier series because it can quote unquote add up over this continuum of frequencies. So note that this x of omega takes on the role of c sub k. C sub k was the complex Fourier series coefficients, and as we went through k, it gave us the amplitude and phase of each of these frequency components. Now as we sweep through omega, x of omega will give us the amplitude and phase of each of the corresponding frequencies as we sweep through there. And the e to the j omega t plays the role of the e to the j k omega sub 0 t. In the Fourier series, as we changed k, we went from discrete frequency to discrete frequency. Now, as we change omega, as we go through this, sweep through this integral, we'll be changing the frequency of that. So that's the idea. Okay, so how do we get this x of omega? Well, same kind of idea that we saw for Fourier series. Remember Fourier series, we took this thing, the e to the j k omega 0 t, smashed it multiplicatively onto the x of t and integrated over one period. Similar kind of thing. We smash these together through multiplication and now integrate, but we can't integrate over one period because x of t is not periodic. We integrate over its entire duration, possibly minus infinity to plus infinity. So this is just like, very similar, almost identical to the equation that we had for finding the c sub k's. And this is called the Fourier transform of x of t. So we say x of omega is the Fourier transform of x of t. Then we use that up here to build x of t in a way very similar to the Fourier series. Now remember, x of omega is complex valued, just like the c sub k's. So we're going to need two plots, one to plot the magnitude versus omega, and one to plot the angle. So that's just like the double-sided spectrum that we saw for the c sub k. We had an amplitude or magnitude spectrum versus omega, and a phase spectrum versus omega. And notice that up here, since we are going from minus infinity to infinity for omega, this will be a double-sided spectrum, just like before. Okay, so to do a comparison between these two ideas, remember Fourier series is for periodic signals, Fourier transform is for non-periodic signals, although later we'll bring the periodic signals right into the fold, so to speak. So just comparing and contrasting these, the synthesis part means we're building x of t. So for Fourier series, we build it by summing up over frequencies. For building with the Fourier transform, this is called the inverse Fourier transform. We are integrating over the frequencies to hit all the possible frequencies. But it's the same idea. At each omega that gets quote-unquote added in here, is a function, we're adding in a function of t, just like we're adding in a function of t up there. And then you can see the similarities in the forms for how we find either the Fourier series coefficient or find the Fourier transform itself. So as we said before, the Fourier transform is complex valued function of omega, just like the Fourier series coefficients were complex valued functions, but there they were a function of k, which took us discretely through the harmonic frequencies that we needed. Again, another view of this, up here we've got the coefficients that are weighting these functions, and we can see the magnitude and the angle give us the amount or the amplitude and the phase shift needed. And same thing down here, we've got our complex sinusoids for each frequency omega, and we're hitting it with a complex number out in front at each omega. So this quantity tells us how much of that frequency there is in the signal at that specific frequency. And again, we need two plots to show these things. Just another graphical idea to help you think about this. We think about the time domain and the frequency domain. So x of t is our time domain representation of the signal. X of omega is our frequency domain. So we use this equation to transform x of t over into its frequency domain representation. And so there are some, well, let me continue on with this. And then going the other way, we have our new model for our signal, this frequency domain representation that just simply tells us how much amplitude and phase we need at each of the frequency components. Once we have that, we can transform it back to the time domain using this inverse Fourier transform equation. So we now have two different models. A frequency domain model is the most powerful of them, and where a huge amount of the engineering is done. So some alternate notations, we can use this notation here to show that x of t and x of omega form a so-called Fourier transform pair. So that just means that x of omega is the Fourier transform of x of t. This notation is just a nice notational idea. It says we take x of t and we apply this Fourier transform operator on it to give us x of omega. So this is just shorthand notation for this equation. That's it. And then the reverse of that, I've got this backwards. These should be those should be reversed. I'll try to fix that. So this should actually be x of t is equal to the Fourier transform inverse of x of omega. And so what that's saying is there's this inverse operator that operates on x of omega to give back x of t. So these are just different notational methods for quickly writing these ideas down. So, you know, in a sense, this Fourier transform x of omega is a lot like looking at an X-ray of something. An X-ray allows you to see what is inside the body, where the bones are, what's being, what stuff something is made out of. X of omega shows us what's inside the signal. It shows us how much of each complex sinusoid we need to build this particular signal. And just to point out, this is kind of pretty much a unique transform. X of t completely determines x of omega, and vice versa. Now the mathematicians will take some issue with this comment, but from an engineer's point of view, that's pretty much the idea. So let's take a look at this, our very first Fourier transform. Remember the rectangular pulse that we introduced? This notation with the subscript tau means a rectangular pulse centered at the origin with width of tau and height of 1. So I don't show it here, but this thing should have a height of 1, which I'm doing a very poor job of drawing here. So this should have a height of 1. My pen doesn't seem to be working very well up in that region. Anyway, so notice our notational convention. We've got a signal little p of sub tau of t. So the case of our symbols is very important, and when you're writing things by hand, you have to be careful about that. Notice that this is uppercase p, so this is not a rectangular function. We have to find out what this thing looks like. So we have a little x of t, and its Fourier transform is uppercase x. So we're just doing that extension of notation for this example. So Now here we're going to directly do this integral that defines the Fourier transform. But later on we will introduce a Fourier transform table where a lot of the classic Fourier transform results are tabulated, and those are pretty much what we'll use to understand some textbook cases anyway. So here's our mathematical definition of this rectangular pulse, and so now we're going to apply that definition. So we're taking the Fourier transform of this rectangular pulse, but remember this thing is 0 outside this interval, so we don't have to integrate outside that, so we can now restrict our integration to that interval. And inside that interval, its value is 1, so there's a 1 in there. And so there's the integral that we need to do. That's not a difficult integral to do. Apply standard Calc 1 results to that. The fact that there's a j up there doesn't change a thing. So there's our antiderivative, so to speak, and then we evaluate it at the limits here. And so when we do that, we're evaluating here and then subtracting, evaluating at the other one. Now the thing that I've done here is I've taken an artificial 2 and put it in there, and I've put a 2 in there. I haven't changed anything because I've put a 2 in the numerator, a 2 in the denominator. But the point of putting the 2 down here is that it sets up Euler's formula. We didn't in the lecture notes state the Euler's formula for sine, but it is in the textbook. So that is the formula for the sine function, and so we can now replace that, and that was the whole point of putting that 2 down in there, is to allow us to use Euler's formula. So that whole thing gets replaced by that sine function. So now we end up with something that looks like this. So there's our result. So we've now found a function of omega that represents the Fourier transform of the rectangular pulse. And now we can look at that and explore what it tells us about this signal. So one thing we know is that the numerator is a sine function as a function of omega. Remember, tau is fixed. We're looking at this as a function of omega. So over omega, that numerator is going to just wiggle up and down sinusoidally, going between -1 and 1. So we've got the sine up in the numerator that's going up and down as a sine between -1 and 1. And we've got the omega in the denominator, which as omega gets bigger is causing the amplitude to decrease, to decay. So we get this kind of behavior. Here's the envelope of 2 over omega. Here's -2 over omega. Because the sign's going between plus or minus 1, it's going to go between plus or minus 2 over omega. So those boundaries show where the function will be bounded, and so that's the effect of this omega in the denominator causes that sine wave to decay like that. So this is what this function looks like, and let's continue on here. As we said, in general we need to do 2 plots, a magnitude plot and a phase plot. Now notice that this Fourier transform is real valued, but we can still view it as a complex number, so we can still talk about a magnitude and a phase. So we charge on, recognizing that a positive real number is going to have an angle of 0, and a negative real number can have an angle sitting over here on the real line, so it's going to have an angle of plus or minus pi, and we can choose either one. So here's the top plot here shows what this thing would look like if we just plotted it as a real function. So we could do that for this special case, but we need to get used to plotting these things as magnitude and phase plots. So to plot the magnitude, It's just absolute value. So everywhere this thing goes negative, it just gets flopped back up. So we see the negative terms get flopped up to become positive. Okay, good. Now what about the phase? Well, let's take a look here. Inside those two vertical red lines, that's the original function is positive, and so a positive real number has a phase of 0. So in that region we plot a phase of 0. But then in the next regions, so in this region here and this region here, the function goes negative, so a negative real number has a phase of either plus or minus pi. So I'm going to choose to plot it as plus pi out here and minus pi out here. The reason that I do that is that I get this odd function. So this is a pathological case where I have to force the odd characteristic of the phase, but nonetheless it satisfies all the mathematical characteristics. Then we go to positive, so we're back to 0, and so on and so on and so on. So that's how we would plot this thing. It looks very nice. Now this function shows up so often, this sine over, sine of omega over omega. This kind of thing shows up so much that there's a actual definition of this function, and it's called the Sinc function. Now, just a warning, there's at least one other alternate version of this without the pi. So sine x over x versus sine of pi x over x. We'll use the sine of pi x over pi x. So if we just look at this sinc of x, we'll see that it has this kind of behavior, and the way that it's set up is it goes to 1 when x is equal to 0. So now at first you might think, whoa, wait a minute, I let x be 0, I've got sine of 0 is 0, pi x at 0 is 0, so I've got a 0 over 0. Why do I go to 1? Well, there is that guy L'Hopital with his rule that says when you have a 0 over 0, you have to take the derivative of the top, derivative of the bottom, and then take the limit, etc., etc., etc. And if you do that, you'll find out that this function really does have the value of 1 at x equal to 0. Okay, nice. So now we can use this defined thing, sinc of x, and use it to get the results, to represent the result that we just had. So here's the result that we started with, and now we're just going to do a little bit of manipulation. Notice that what we're really looking for in the sign is pi times something. So let's get a pi in there. We need pi times something, so we put in a pi over pi. Haven't really violated anything. I'm allowed to do that. Pi over pi is 1. But then that allows me to take the bottom pi and group it with the 2 and leave one of those pi's out in front. Aha! Now I've got pi something. So that something is playing the role of the x. So what do I need down in the bottom? Pi times that same something. So let's get that down there. So I'm free to again insert something over something, and I did that specifically so that now regrouping, I end up leaving this pi out there and grouping all of that together, and lo and behold, that is the same thing here. But I've done something else. I've canceled that 2, canceled that pi out in front, so I'm just left with the tau. So we can now write this as tau times sinc of omega tau over 2 pi. So there's our final result. It's a nice thing. It shows up on this Fourier transform table that we're going to see in just a few, I think in the next lecture, maybe the next 2 lectures, something like that. We'll be talking about a Fourier transform table. So here's summarizing our result. In the time domain, a rectangle transforms to a sinc, and this is our view of that sinc in a spectral plot. So this is our spectrum, double-sided. For Fourier transforms, we are almost always talking about double-sided, although because of the symmetry for both magnitude and phase. We can just show one side, and you can infer what the other side looks like. So this amplitude spectrum, that's telling us how much amplitude we have at each one of these frequencies. So what this plot is telling us is that at frequencies down here, for this particular example, down below like 10 radians per second, we have quite a bit of content. But up here around 60, 70, 80, much less content, meaning we need less of those frequency components to create this signal. But nonetheless, we do have some components up there. And notice that we have contributions from virtually every frequency with the exception of a handful of things. In fact, we have just a discrete set of points that are left out. But other than that, we've got a continuum of frequencies that are contributing. And then the bottom plot, a little less important, but important to get the full picture, tells us what phase we need at each frequency. So there you have it, Fourier transform of a rectangular pulse. This is what I would call a cocktail party result, something that you should just know. Hey, Fourier transform of a rectangular pulse? Sinc function. That's kind of the extent of what you need to know off the top of your head. So anyway, we'll continue on with more Fourier transform stuff, and this is really one of the big workhorse tools that we will be using for the rest of this course. Thanks.